It's 2 a.m. Your pager goes off. The merchant dashboard is totally out of sync, and you're just staring at a wall of logs trying to figure out why a critical system integration is failing silently. Sound familiar? Well, welcome to this explainer. Today, we're tackling the very architecture of system integrations. We're diving deep into how disparate platforms actually talk to each other when state changes. If you manage, support, or build IT infrastructure, you know that understanding the mechanics behind these data flows isn't just nice to have, it's absolutely non-negotiable.
So it's the classic IT support nightmare, isn't it? Hey, why are my payment notifications delayed again? Or why is this data missing from the CRM? These delayed syncs and missing data points are, honestly, some of the most hair-pulling pain points we face, and they usually stem from a fundamental mismatch in how systems handle event data. So that really sets up the practical troubleshooting journey we're about to embark on today. We need to pop the hood and look at data synchronization.
Here's our roadmap for today. First, Webhook versus polling API. Second, polling and its limitations. Third, webhooks, the push model. Fourth, HMAC signature validation. Fifth, inspecting with webhook site. And finally, we'll trace a missed payment. Section 1, polling and its limitations. So how do two completely different systems actually talk to each other when a state change occurs? Well, for years, the default answer was API polling. Polling is basically a client-driven synchronization mechanism. Essentially, your system is the client, and it's constantly walking up to the source API, knocking on the door and asking, hey, do you have any new information for me? How about now? What about now? You maintain full control over the schedule and the retry behavior? Sure, but as we'll see, that control comes at a pretty steep cost. And this right here brilliantly illustrates what happens in a polling architecture. I like to call it the stuttering effect. At minute 1, you ask for data. Empty response. Minute 2, still an empty response. Minute 3, finally, you get the data. But look at the inherent latency we're dealing with here. Your data is literally only as fresh as the interval between your requests. If a critical payment event happens, say 1 second after your polling cycle begins, your system remains completely oblivious to that event until the next cycle rolls around. Which brings us to this absolutely staggering number, 95. In high-frequency polling systems with sparse updates, over 95% of requests return absolutely empty. Just think about the sheer waste happening there. You're burning through API rate limits, exhausting CPU cycles, performing TCP handshakes and TLS negotiations, all for a simple 304 not modified response. It is incredibly inefficient.
Section 2, webhooks, the push model.
Okay, so what's the architectural cure to our polling latency problem? Well, here is the direct contrast. On one side, we have the exhaustive API polling poll model. It's synchronous, it's outbound traffic, and it suffers from high latency. On the exact opposite side, we have webhooks. This is an inversion of control. It's a server-driven push model. Instead of you constantly asking for updates, the source system actually takes the responsibility of initiating communication the exact moment an event occurs. Think of polling like obsessively refreshing a web page, whereas a webhook is like getting an immediate text message notification on your phone. It's asynchronous, requires an inbound endpoint, and it happens in near real time. Now, don't get me wrong, polling isn't dead, not by a long shot. There are definitely environments where the push model just doesn't work. For example, if you're operating in a highly firewalled or isolated network environment, you can't exactly expose the public HTTPS endpoint required to receive a webhook. Polling is also the unshakable foundation for heavy batch processing, nightly financial reconciliations, and audit recovery. If your webhook receiver goes down for whatever reason, a scheduled polling job is your trusty safety net to backfill any missed events.
Section 3, HMAC signature validation.
Here's the thing. If you're using webhooks, you are exposing a public endpoint to the internet, and that requires a mandatory lock on the door. Enter HMAC, which stands for Hash-Based Message Authentication Code. It's basically the industry standard for securing webhooks. Because your endpoint is public, anyone could technically fire a payload at it. HMAC uses a shared secret key to generate a cryptographic signature. When you verify that signature, it confirms two absolute truths. 1, the payload truly originated from the trusted provider, and 2, the message hasn't been altered in transit by some man-in-the-middle attack. Let's look right over the shoulder of the provider sending the event. First, they perform canonization, which is just a fancy way of saying they package the HTTP method, the timestamp, and the raw payload. Second, they run that string through a hashing algorithm, typically SHA-256, combined with your shared secret key. Finally, they transmit that resulting digest, the signature, inside a custom HTTP header, often called something like X signature or Stripe signature. Your receiving server then just runs the exact same math in reverse to verify it. Simple, right? But a signature alone isn't quite enough. You really need defense in depth. When verifying HMAC, always use a constant time comparison function to prevent timing attacks. And to stop replay attacks, where a hacker intercepts a perfectly valid webhook and just resends it, you need to implement a 5-minute timestamp tolerance. Anything older just gets rejected outright. Furthermore, enforce IP allow lists based on the provider's official documentation. This filters out malicious scanning traffic at the firewall level before it ever even hits your HMAC verifier. Oh, and of course, make sure you rotate those secret keys regularly.
Section 4, Inspecting with Webhook Site. Now let's transition from theoretical security to immediate practical debugging. When an integration breaks, you need industry-standard inspection tools. I absolutely love this quote because it saves so much wasted engineering time. Before you write a single line of handler code, you need to see what the provider actually sends. You literally cannot rely solely on documentation. You need a webhook inspector, a tool like webhook.site, request-bin, or hookdeck to capture the raw, unformatted request. These tools give you a temporary public URL that catches the payload without any of your local firewall or application friction getting in the way. When you capture a test webhook in one of these inspector dashboards, this is exactly where you should be looking. Don't just stare at the JSON body, look at the headers. You need to identify the content type, find the exact name of the X signature header, and locate the X timestamp. If your local code is failing to validate a signature, I'd say 9 times out of 10, it's because your framework altered the raw body payload before verifying, or you're just looking for the wrong header name entirely. Section 5, Trace the missed payment. Okay, let's put this all together with a real-world simulation. Say we have a merchant complaining that their application isn't showing an approved payment. Looking at our system logs, we can identify the missing trigger. We're expecting an approved payment webhook event from our payment provider. Let's say it's the Payably API. This webhook is supposed to confirm manual charges in real time, but our system never processed it. So what happened? Did the provider fail to send it, or did our system reject it? Well, here's the exact step-by-step workflow a senior IT engineer would use to isolate this broken integration. Step 1. Generate a unique webhook.site URL to bypass our local servers entirely. Step 2. Log into the provider dashboard and temporarily update the webhook config to point to this new test bin. Step 3. Open Postman and trigger a manual test payment to force the event. And Step 4. Go back to webhook.site and inspect the captured payload. If the payload arrives perfectly at webhook.site, the provider is totally fine, and the issue is likely a 401 unauthorized error or a failed HMAC verification on our own servers. Let's zoom in on that raw JSON payload we just captured. You see the event type, the amount, the status, but look right here, the item potency key. This little guy is a lifesaver. Because webhooks travel over the public internet, network timeouts happen, and providers will often retry sending the exact same webhook multiple times. By tracking this unique item potency key on your end, you ensure your system only processes the payment once, preventing you from accidentally crediting a customer twice for the exact same transaction. Talk about dodging a bullet. To wrap up our troubleshooting journey, we arrive at the gold standard for system architecture, the hybrid resolution. It's essentially a webhook-first, polling-second architecture. Webhooks drive the real-time customer experience and immediate automation. But you still run a background sync engine that uses polling to periodically audit for discrepancies and catch any silent webhook failures. You rely on idempotency keys to manage network retries safely, and if your team is constantly struggling to test this locally because of expired tokens, fix your environment drift by automating your auth tokens directly inside Postman using pre-request scripts. Which leaves us with this final, critical question to consider about your own integrations. Is your infrastructure truly balancing the event-driven speed of webhooks with the unshakable reliability of polling fallbacks? If you're relying entirely on just one or the other, it might be time to audit your architecture before your pager goes off at 2 a.m. Thanks so much for joining me for this explainer, and hey, happy troubleshooting.